everyone. So pleasure to be here and have a chance to give this talk. My name is Sheer El Showk, and I'm the CTO of Lore AI, a company doing machine learning for mostly text analytics based in Paris in the US. And this talk is going to be, in some sense, our autobiographical journey through our attempts to build out this system. It's going to be pretty high level. I hope you're not looking for a lot of details, because I'm going to try to cover a lot of ground. If you feel you're missing on details and you're interested, please come ask me afterwards. I'm very happy to talk about it in more detail. But I'm really going to try to go through sort of, what problem we try to solve, our journey towards solving it, and the lessons we learned along the way. And I think some of these experiences are quite common for many startups trying to set up machine learning. In particular, we work in natural language processing. So ML is machine learning, NLP is natural language processing. But I think our experience is kind of common, and there's a lot of interesting lessons that we learned along the way, and the solutions were not always easy to find online or in other places, so I'm going to try to share that with you. But it's not going to be very detailed, so if there are details you want to know, just either interrupt me or ask me afterwards. But always feel free to interrupt in any case. So Lore is a small startup. We're focused basically on delivering, on developing machine learning solutions to solve a wide range of business problems. Our focus is very much text analytics. Ultimately, we have built a product, we are product focused, but we also have to provide a fair amount of consulting services. I mentioned this in this talk because, as you see, the reason I bring this up is that I'm going to try to show you how we built a tool or a stack that allowed us to do all of these things quite flexibly. That's why I'm sort of bringing all these things up. And I think, the lessons that I'm going to promote in this talk, in some sense, it's kind of a follow-up to the keynote this morning where we were told all these things about what you should and shouldn't do in a production system. But they're really going to be useful for people in a similar situation to us. They may not apply as well if you have a giant company with very different constraints. So in particular, we need to be cost effective. We need to be able to do things without having to pay a huge amount of money for them. So we need to compute efficiently because we have very large computational needs. But we also have to be flexible because we don't necessarily know how our business model might change from day to day. If you're in a startup, it's probably a very familiar idea that your requirements might change quite quickly. So we really had to develop a set of tools that allowed us to deal with, to be both cost effective and flexible at the same time. And an even further constraint is that we had customers come to us sometimes asking us to be able to process large amounts of data. So we also had to be very scalable. So doing all of these three at once is difficult. And I'm going to try to explain to you how we managed to get there, hopefully, to some degree. A second set of challenges that we had to contend with, the fact that we're kind of mixing two worlds. On the one hand, we are focused on machine learning and natural language processing. So there's a large, very vibrant ecosystem of these tools in Python. And I should also say we're entirely Python-based. So another aspect of this talk is I want to say that you can do everything you need to do in Python. This idea that once you get to a large enough scale, you have to go to Java, that's bullshit, frankly. And I'm going to try to propose, I will give this talk, and I'll even reference other talks that say similar things later on. So Python has a very nice, in fact, probably one of the richest ecosystems here. It also has a very nice ecosystem for standard web stack, databases, caching, all this sort of stuff. But mixing the two together is not completely straightforward because they come from different worlds a little bit. And trying to do it in a way that's fully scalable and manageable by a small team, without incurring huge amounts of cost, that's really a challenge. And so that's what I'm going to tell you what we managed to do and a little bit of how we managed to do it. And just to sort of advertise a little bit, combining all of this, we've managed a small team in a not that long time to really put out several very different products. So, we've built a chatbot, we've built a content-based recommender engine. So it was a little different. There was a talk this morning about recommendation systems. There, the talk was really collaborative filtering. Here, the idea is really text-based, understanding the text users consume and using that via machine learning to understand things about the users. And then finally, our flagship product, which we call Salient, which is really a document analysis system. So I'm not going to spend a lot of time talking about this stuff. I'm going to talk about the platform that underlies all of these tools, but it's the same platform that underlies them all. And I think that's another lesson I want to try to convey, that you can build a lot of different tools on one platform if you build the platform in the right way. So the first thing I'm going to talk about is the actual, what it is that our system does, the task that we're trying to solve. And then I'll talk to you about the problems that we face, and then hopefully the lessons we learned in trying to solve them. So this is the general task we're trying to solve. So we have a client come to us with data. And for us, data means something quite specific. One of the things we really focus on is taking unstructured data, like documents, PDFs, OCR documents, whatever they are, that really don't have a lot of structure. It's just a bunch of text. And also, at the same time, taking structured data. So clients may have, for instance, their client database or a list of products they're interested in or whatever. And taking these two and combining them together, so understanding, where, say you have a bunch of documents that mention, for example, names of products or employees or competitors, making the connections between them, and then allowing you to use machine learning to analyze them. So that's really what our system does. And the way it does it is, you take these documents, you upload them into the system, these get converted and parsed into a standardized format. We use JSON internally, and I'm a huge fan of JSON. I think it's just a very natural way to represent data. The first stage is basically standard NLP processing. If you're familiar with natural language processing, these terms should be very familiar to you. If not, I'm happy to explain them later on. But basically, we extract out the grammatical structure of each sentence. We look at the different parts of speech, whether it's a verb or a noun. We extract names of people or companies or whatever from the data based on the grammar. So if you're familiar with a bit of machine learning, these things should sound quite familiar. If not, again, I'm happy to explain it later on. And the output of this process is basically a very annotated version of these documents. So the documents are broken into paragraphs, paragraphs are broken into sentences, sentences are broken into words, and words are labeled with all of these things. So it's a really deeply enriched version of the input. And then the next step is to say, okay, we have these very enriched versions of the documents. Let's make connections between these documents and the data that we have available to us. So we have this thing called the knowledge graph. You may have heard of this notion from Google. They've been promoting this idea, but it's an idea that predates Google, I think, in any case. It's a way of representing information in a structured, arbitrary information in a structured way. So for us, the knowledge graph includes everything inside Wikipedia, but also potentially client data. So clients may give us lists of their products, their competitors, whatever, and we just make connections between the documents, the unstructured documents here and the structured information here. This all goes into some data storage tools, and then the clients can basically access the annotated data, but also provide a bunch of machine learning tools on top of that. So we do things like question answering, so you can ask a question and the system tries to find the answer inside the documents, or looking for document similarity, or maybe extracting information. So you say, I have thousands of documents, I want to extract information like the relationships between which employees talk to which client, that kind of thing. So this is the basic task we're trying to solve. And you can see there's lots of parts of the system, and there are lots of moving parts here. And we solve this task, we solve it at scale, and we solve it using, I think, best of breed Python tools, and a lot of stuff we add ourselves. And I'm going to try to, essentially, most of this talk is going to be an advertisement for a lot of the tools that we use to get here. Many of you are probably familiar with most of those tools, but I think maybe some of them are not as promoted as they should be, or not promoted in the right way, let's say. So just to give you a brief idea of what you can do with this kind of a pipeline, I'm not going to go into a lot of details here again, but the things you can do with things like managing giant databases of contracts, extracting information from these documents, linking them to your clients. This is obviously a kind of thing you can imagine doing with a stack like that. Analyzing news, if you have a year's worth of news, you want to extract information about your competitors, about products you're interested in, or about whatever. Patent analysis. So it's really a large set. I guess the important thing to say is that this general pipeline really allows you to process, to address a large number of business problems using one framework. And that's what we ultimately ended up building, though we didn't initially start doing that. So that's the task. I'm going to switch to telling you a little bit about what I think the challenges are, and then how we managed to go around solving them. These are, in some sense, standard challenges, many of them. Many of them are just challenges you'd have anytime you try to build a large application with Python. There's a set of standard solutions. You want to parallelize, you want to make sure things are scalable and redundant and everything like that. But then there are additional problems coming in when you start trying to also use machine learning, because again, the tools there are maybe not really as designed with production in mind, because machine learning is really the sphere of, say, data scientists and people who maybe would open up an IPython notebook, do some analysis, and the same thinking has not been applied necessarily to those as to building a large web stack. So one of the first and maybe focused problems that I'm going to talk about a lot is basically scalability. We had clients asking us if we could process millions of documents. This starts looking really big. You can't even fit these millions of documents on a single server. So you automatically have to be at a point where you can parallelize and do something at scale. We have ourselves internally a large database of news which we provide services on. This has been mentioned already this morning, but Python has this reputation of being slow, which is true. Python is in some sense definitely slow. But you could even say it has a bigger problem in that it's a bit hard to parallelize. There's the whole issue with having a global interpreter lock, and there are ways around it, but actually when you start doing machine learning, some of those ways around it don't really apply anymore. So there are additional problems that come in. And so, I say there is definitely this notion, I've had people tell me that, when you try to do things at scale, you should really go and start using Java. And actually, to be honest, if you look, the products that do this kind of thing really at scale, they almost all do use Java. So I really like to claim you don't need to, and explain to you, there are ways around all these problems, and I'm hoping that in the future, we'll see more and more of this done in Python. And I think there are a lot of tools I'm not going to mention, things coming out of Continuum Analytics like Dask and Blaze and stuff. If you haven't heard about these are also very interesting tools that are trying to replace the idea that only Java can do enterprise scale, stuff, basically. And as I said before, machine learning brings a lot of its own problems. So to make that more concrete, in machine learning, you often will have very large models. You'll have, for the system to even do an analysis, it will need, maybe a matrix in memory that can be gigabytes large. That's fine if you're then just doing it with one core, but now if you start wanting to say, okay, well, I want to run 10 of these in parallel because I have 10 cores, well, now you need 10 copies of that matrix if you're doing something like multiprocessing. So these are the kinds of problems that come up when you try to do this in something like Python. And you also just need to be very performant. And often, while the core of the code in Python still ends up very performant because it uses either a GPU or some very optimized NumPy code or whatever, there's often a lot of pre-processing that has to be done, and that is not necessarily performant, and often that's actually the real bottleneck. And that has to be done in usually native Python or whatever else you're using. So that's one big issue. Another one, which I kind of alluded to a little bit, is maintainability. So one of the things is that we use different sets of tools. The machine learning stack is tools like Theano, Gensim, and Spacey. These come from a very different world than things like Django, Celery, and MySQL, which are usually designed to work together. It's not that they're incompatible, it's just that there isn't as much literature out there on how to run Theano in production, for example. It's just not something that the people are as familiar with. And again, we're also a small team, so having to try to combine all these things at production, where you have to have multiple servers and managing them all, can be very difficult in terms of DevOps. And so I don't think the solutions I'm going to tell you are going to be a huge surprise. I'm maybe just going to emphasize what did and didn't work for us. The last thing to say is also that on top of maintainability, you also need to be very flexible. You really want to, we don't know at any given time what a new client's going to ask us. We have some set of products, but a client might need some different requirement. So it's very important for us to be able to do something, to change what the stack is aimed at doing, and to add new parts, to modify it very quickly. And also sometimes, there might be another solution that's not yours that works just great, and you just want to be able to add it into your stack easily. So there's a variety of things like that. And also just being able to deploy the solution at scale quickly without a lot of energy. And in the early days, this was really a big problem for us, and now it's not at all. And I'm going to tell you sort of how we got there. So that's what we try to do. And I think for me, a nice way to explain this is to tell you where we started, and then where we are now, and how we transitioned from one to the other. So again, I think this is probably reflected in a lot of small startups and the way they work. So where we started is probably somewhere which a lot of you have been. You have an application in mind, you try to build it, you do it the fastest way possible. I think the speaker from this morning also alluded to an idea like this. Just do the fastest thing you can. Build everything in a monolithic Python server, maybe even use some PHP for the UI if you're really lazy. Single database backend. You hard code a lot of dependencies on the exact problem you're trying to solve at the time, rather than building something more general. We used a lot of off-the-shelf tools that weren't even particularly high quality. So if you are not familiar with the NLP world, you may have heard of NLTK, which is a Python toolkit for natural language processing. It's kind of the first go-to thing, and a couple of years ago, it's more or less all that was available. But right now, it's really substandard. So we used it initially, but now I would definitely recommend people to not use it. It's way below the quality of what else is available in the open source world. We had a completely serial pipeline. We couldn't parallelize it really at all. There was no redundancy or scalability. And I think, in some sense, the straw that really broke the camel's back was trying to maintain this system in production. So we had some servers that were running databases that got very large, and it got to the point where we basically couldn't even migrate or change things because it was just too much of a pain. It was sometimes running old versions of the code, and it was just very painful to try to do anything with it. So that kind of pushed us to invest a little energy in learning modern DevOps, rethinking architecture a little bit, and that's basically what I'm going to talk to you about. So, we had several pivots. Our initial idea didn't turn out to not be very good, so we tried some different things. We also had some clients come to us with particular needs, and this forced us to do some different things. And I guess from a sort of business perspective or business development perspective, business/development perspective, what I want to point out here is that we didn't just repeat the same mistakes. We tried to take the opportunity to say, people come to us with new requirements. Rather than just building out to those requirements the same way we did in the first go, we took what we had and we said, can we refactor it in a way that's much more general and can solve the entire class of problems we've seen? And we've constantly tried to do this. So this is why we have a stack, not just a single product. And I think that's actually kind of a nice thing to do. It takes a lot of energy up front a little bit, but it solves a lot of problems down the road. I think, by the way, you'll find my talk is in some sense a lot like the talk from this morning, the second keynote, with maybe a little bit more details thrown in a specific use case. Because I think a lot of the things he said do kind of come up here again. I didn't know about his talk when I wrote this. So this is our new stack. It's a much more sophisticated looking beast. I think one of his comments this morning was not to over-engineer. I'm afraid we can definitely be accused of having done that. But I would claim that in our case, over-engineering has made our lives insanely easier than under-engineering. So I don't completely agree with this claim of not over-engineering. So this is what the modern stack looks like. It's much more sophisticated, scalable, manageable. It's much easier to use, actually, than the old one, even if it looks much more complicated. So the first lesson, and I'll say this again and again throughout the rest of the talk, if you're not using Docker and Kubernetes or something equivalent, you should be. There's just absolutely no excuse to not use modern DevOps. However hard you think it is, once you've made the jump, you will look back at the rest of your life and think it was a waste of time. It's really, you waste so much time on things that these things solve for you. And I'm going to emphasize this in many different ways, and not even the obvious ways. There are really many ways which these tools solve problems for you. Likewise, well, maybe as a consequence in some sense, we use nice modern tools like Celery for parallelization. I'd say this is the kind of thing that had I not had Docker and Kubernetes around, I wouldn't have been able to do or wouldn't have wanted to do. But because we use modern orchestration tools, it's much more manageable. And we also sort of architecturally switched from a monolithic architecture to something that's much more microservices based. And I'll try to explain a little bit what I mean by this and how I think concretely this can be a useful thing. So in our system now, you have a load balancer. All this stuff is kind of part of the Kubernetes stack or even part of Docker or Docker Compose. You come hit it, you have Django instances for the input, and then you have a bunch of Celery workers that basically use a bunch of microservices. So each of these things are things that can do a specific task, and just a specific task in a very nice way. It's kind of like an API, but I think there's a distinction to be made between a microservice and an API. Okay, we replaced also other NLP engines with our own one, and we use everything here is stateless, and that's really essential because that's important to be able to make it scale and be usable. All the state is maintained in a bunch of well-known services that provide state. Redis, I'm sure many of you know, Mongo as well, and MySQL. One that probably is less well-known, and I do want to advertise a little bit. I have nothing to do with it, but I think it's nice. It's called Minio, and it's basically an S3 compatible service that you can launch inside of your Kubernetes or Docker stack and provides blob storage. So there isn't really, there aren't really many good solutions for blob storage, and this is quite a nice one, so we use that. I hope this picture sort of convinces you the stack is very modular and reusable. What's a bit surprising is that it's also extremely rapid to deploy. So getting this whole thing up on a machine, on a single machine, takes minutes. Getting it up on a cluster takes tens of minutes. But that's really how complicated it is to set this thing up. It really takes absolutely no time to set up. And that's a big distinction from this much simpler setup, which looks much simpler. Okay, this diagram doesn't do it full credit, but this looks much simpler, but this is actually very hard to maintain because you haven't sort of converted DevOps into dev in some sense, and that's what these things really let you do. Okay, so this is what the stack looks like, and I'm going to now try to tell you the lessons we learned along the way in a bit more detail. Still not a huge amount of technical detail, I'm afraid. So these are the main lessons I'm going to go through. One, again, I think this lesson is really so important because many of the other lessons would not even be possible had we not gone down this road first. So again, I don't even install anything on my computer anymore. I install it in Docker and I run in Docker. I develop an IPython notebook that's inside of a Docker instance that's connected to the rest of my stack. That's how important it is, I think, to make this transition. Also, it's actually, what I want to try to say is it's actually very easy. There are some really amazing parallelization libraries. There's even going to be a talk, I think, in this conference about joblib. And I've used many of these libraries, and they're all very powerful. They all have some give and take, but actually for most use cases, I think they're more or less equivalent. And so you should definitely take advantage of them. And they're not really hard to set up. That's the surprising thing. Another lesson I'd like to suggest is that it's very important to try to write your code in terms of a notion of stateless microservices. This is something we had to refactor our code to get it towards, but once you've done this, combined with parallelization and with the good DevOps, you essentially have scalability. Well, with this last piece as well, but essentially you have free scalability. You can just make your stack as large or small as you want. You become fully elastic. And to finish that little set of things, you basically need scalable persistence as well. So you need some notion of distributed persistence and caching. This is not something you want to do yourself. It's a complicated problem, and there are great solutions out there, so you should use them. So I'm going to talk about these things, which are really the sort of underlie the architecture of our stack in a little bit more detail, and then just some patterns and performance tips that have come along the way. So there's this pattern that I find that's very useful in terms of future-proofing your code. I'll talk about it a little bit, and then maybe just some more detailed performance tips I have as we've developed our code. Are there any questions? I know I speak kind of fast, and yeah. Yeah. No, there are. I mean, so Spacey is an amazing library. Spacey. I'd be very happy so Spacey is, I mean, right, you know, it used to be that there were certain tasks in the NLP world that you could only do in Java. So, you know, there were some great Java libraries like Stanford Core NLP and Emory NLP. Spacey is, so this is how people, so Core NLP parses a few hundred sentences per minute or something like that. Spacey parses 13,000 a second. So, and it's this Python library. So I think, you know, and it scales much better. So these are the kinds of things that I think are changing very quickly. Was there another question? Yeah? No, our stack is not at all open source. I mean, we use a lot of open source. We are a small startup. Our stack is what we sell, basically. Someday I would like to very much open source large parts of the stack. In fact, I think we will down the road, but it's for right now, it's really what we're selling. So, yeah. Yes. We don't particularly focus on the parsing. That's something we use more as off-the-shelf stuff for. We focus on the second part of the pipeline, which is analyzing and the language part, not the format part. So if you want to parse, there's TextTract. I don't know if it's a library. It's a Python library. It's an open source Python library. It wraps 10 other or 20 other Python libraries. It parses more or less, I think, to first order anything. The quality is a bit hit and miss depending on the library you use. Down the road, we probably try to implement a machine learning-based solution based on images and stuff, but we're quite far from that now. Sorry? No, we're in an early phase. We have a couple of customers. We have a lot of, we're doing a lot right now, but we are really a very early stage startup. I'm happy to talk to you more about it later on, but I'm not going to talk about it yet. Yeah, so, I tell customers we process any language, and it's not completely inaccurate. In reality, there are different parts of the stack can do different things at different levels. So core European languages we can process. Non-European languages become harder. So some parts of the stack will work in any language. Other parts, we have specific constraints in languages. So Spacey, for instance, can do various things in various languages, but really the two languages it's most strong in are English and German. Adding additional European languages is usually not too hard for many of the tasks, but beyond that, the pipeline involves many different pieces, and you have to make sure you have them all covered in the different languages. Please feel free to interrupt with more questions as we go along. This I'm going to introduce this term. I'm not sure if anyone's used it before, but Dockerize early, Dockerize often. I feel like I emphasize this so much because it was a mistake I made. I took way too long to do this. I just kind of thought I'll learn Docker eventually, whatever. But when I finally did, it was a complete change in the way I worked. And if you haven't, I think if there's one thing to take away from this talk, it's that you should use Docker and Kubernetes. It's not Docker in particular. It's the notion of containerization. It really changes the way you work entirely. And in more than ways than the obvious one. So there's the obvious one, which is that your development environment becomes uniform. All developers now can essentially work on the same virtual environment. You all know that you're going to be able to do the same thing. Something just to point out is, especially with Python and IPython, it's quite nice because if you have some complex stack that maybe involves many different services, you can launch the entire stack, and you can launch an IPython server in the stack, and then from a web browser, you can be coding inside your own stack. And I use this frequently, and it's really quite nice. But I think actually the most important part of Dockerization is not this part, which is what everyone thinks about a lot. It's the fact that it changes the way you think about your platform and your code entirely. So in the past, when it comes to Celery, for instance, which I'll talk about in a slide or two, it's a complex beast. If you look at Celery, you have to install a broker service. You have to set up a bunch of things. It takes a fair amount of work, and I didn't want to add that overhead to my DevOps, so we didn't use Celery initially. Once you use Docker, Docker Compose, Kubernetes, those problems become much easier to solve. Usually someone has already built a Docker image with whatever service you want to use. It's a one-line change to your Docker Compose file to add that image. Suddenly it's part of your stack, and now your code can assume that server is always going to be there, whether it's on your dev machine or on a production machine. So what it means is you can convert dev problems into DevOps problems. You can say, Whereas before I may have had to find some way around this myself, implement parallelization manually. Now I can simply install, if someone else has some awesome service that does something, even if there's some overhead to setting it up, once I solve that problem once, it's solved indefinitely and I'll never think of it again. So it really changes the way you set up your stack. And so to make that point clear, our stack is extremely fast and easy to set up. This is how I launch our stack. It's a single line command. It launches a bunch of different services. You'll see here, there's Celery, there's Sphinx, there's all these different tools that if I had to do this on my own machine all the time, constantly make sure that my laptop had all of these services available, properly running as I upgrade, it'd be a huge pain. I don't have to do that. These services are constantly around in exactly the state I expect them to be. So I can launch, whenever I'm developing or wherever I am, I'll have all the things I expect to be there. So the services really become part of your own product in some ways. So I'm sure for the people that know this stuff well, I'm saying boring things, but if you don't, I really do suggest you invest some energy into looking into them. Another thing which is kind of nice if you're a cheap, small startup, and you happen to enjoy administering Unix machines, is that you can cut your costs a lot by not running on AWS, but by running on bare metal. So we have a bare metal provider. Again, I'm not particularly advertising them, there just happens to be the people we use. But if you compare the same essential machine in AWS, it costs about $360 a month. With them, it costs $70 a month. And this is a lot of hardware you're getting for $70 a month. And using something like Kubernetes, Kubernetes is a lot more complicated than Docker, but once you learn to set it up, you basically have all the benefits you have of AWS, but in your own stack. You can launch an arbitrary number of containers, you can have virtual networks, you can have load balancing and all sorts of traffic routing. So there's really a very nice ecosystem here, and this has nothing to do with Python, but I'm going to promote it very strongly nonetheless. Okay, so the second, yeah, please. So right now I'm using, what am I using? Not Weave, I'm using one of the other ones. I've forgotten the name, the default Flannel. But actually, so one thing I learned to my shock recently is that most of the CNI, so Kubernetes lets you install a virtual network over a large cluster of machines. Weave is one of them. Flannel is sort of the default one. None of them encrypt the traffic, except for Weave, it turns out. This was shocking to me, so I will be switching to Weave soon. But yeah. So parallelization. So this is something which I think if you're going to scale, you really need to solve this problem well. And as I said, there are many nice solutions. And in fact, this is not really part of the talk, but I would highly recommend people to look into Dask and in fact the entire Continuum Analytics environment. I have nothing to do with Continuum Analytics. I know they're probably a sponsor, but they've been developing a lot of nice tools, essentially try to replace the Spark Java world dominance with a Pythonic version. So they have Dask distributed, Blaze is kind of like a distributed version of Pandas. So there's really a nice ecosystem here, and we did start using this. It's a little less mature than Celery, so ultimately we ended up for Celery, but you could really use any of these tools. They're really all quite nice. They have, IPython has built-in parallelization, which has now been spun off into its own project. So, the point is that for simple use, they're all more or less the same. When you try to do more complex things, they're a bit different. Initially, I avoided Celery because it was too complex. Ultimately, I switched back to it because once I've had Docker and Kubernetes, it became easy. I set it up once, and I didn't care anymore. And just a more concrete note, if you are using Celery, it can use various different brokers. I would recommend using Redis if you want low latency. I tested it, and RabbitMQ has much higher latency. But I guess the main point of this slide is that although these things sound complicated, it really took me almost literally 10 minutes to parallelize our stack. I just said, what are the functions that I call? What are the main functions I'm interested in? I just go and I write a little wrapper around them, which just says, hey, do this thing in parallel. So rather than just do this thing normally, I call it inside of something that's wrapped in a Celery decorator. And I even added a timing call just for, because I could. And now suddenly, whereas this code before used to run on a single machine, I couldn't parallelize it, now I can just spin up 20 Celery workers and throw it on the task queue, and this runs. And it's really, yes, of course, this isn't the entirety of the code. There's a little bit more code, but we're really talking about one or two small modules with maybe 30, 40 lines of code between them entirely. Most of it copied and pasted out of the Celery tutorials. Of course, for this to work, it's very important that the things I'm going to say on the next slide already hold, which is that your tasks, your data should already be stateless, and any state you need should already be maintained in an underlying distributed persistence layer. So all of this is only possible once you've solved some other problems, which I will talk about in a second. But once you have, it's really easy to do this. Okay, so this is an abstraction. I'm probably misusing an existing, I mean, I know microservice is an existing term. I'm not even sure what the official definition is. I'm going to give you my definition and the way I think about them, because I think there's a very useful way to think about programming in this kind of, you know, there are specific constraints that come from trying to run in this kind of environment. And for me, microservices solve these constraints, or that's how I define microservices. So in some sense, I like to think of microservices as a generalization of the notion of a Python notion of an abstract base class, or if you're a Java person, of an interface. You say basically, a piece of my code is there to solve a particular problem. I'm going to just set it up to solve, I'm going to define an interface, literally define an abstract base class that says what is it that this piece of my code is supposed to solve. And then, you know, down the road, I can implement that many different ways. I can even use a different back-end service for it. I don't care. The microservice just provides that service. So, you know, I guess I'm going to tell you a lot of the things microservice is not, but this is the thing that it is. So, you know, we have, for instance, microservices for NLP tasks, for logging, for database persistence. But another way to think of them is that, you know, we use Redis for caching, but rather than calling it Redis, we define sort of an abstract base class, which is a key value cache. So it's something we say this is a key value cache. I'm going to put a key in it and get a key in it, and get a key back from it. That's the functionality it provides. And then I define an implementation that uses Redis as a backend. But the rest of my code doesn't use that implementation. It uses this microservice sort of interface. And this is, I think, a very nice way to build your code because it makes things, it separates out concerns very well, and it makes things very flexible down the road. What I also want to maybe make a distinction is that a microservice, well, it should be stateless. That's really, in some sense, a constraint that comes from the fact that you want to run them many of them in parallel as easily as I showed you in the previous slide, and in an environment like Kubernetes where you really can't be guaranteed that any of the services running is going to maintain its state. If you don't know much about Kubernetes and these sorts of things, there's a big difference between running a stateful application and a non-stateful application in Kubernetes. You can run stateful ones, but it's a lot, you have to pay special attention. So it pays to make as much of your stack as stateless as possible. So what this means is that, you know, if you do anything, even like caching inside your code, if you have a dict that sort of caches user responses, rather than keeping it in your code, you should use some external service like Redis or a database or whatever. And I guess what I also want to emphasize is that to me, a microservice is not a microserver. It's not to say I have some little part of my stack with a REST API that solves one problem. You can do that, but this adds unnecessary overhead in terms of the interface. You know, sure, I could put my NLP services in their own server with a REST interface, but why? I mean, I may want to have a lot of different applications that use that same service. So I can take that interface and just keep it in Python and reuse it in many different applications. So for me, an application is something that really combines a bunch of microservices and have them talk to each other. And if there's a reason to, of course, I can put them inside of something with a specific interface, but that's not the definition of a microservice to me. It might be the definition in a more standard usage. I'm not sure. So to me, in some sense, they're just APIs within an API, but they really should have all the features of an API, encapsulation, hiding the underlying implementation, and everything like that. OK, and so for all that to work, you also need something like distributed persistence. So I'm going to take an opportunity to explain what I mean by this, and maybe also give you a bit more of a concrete example of how we use this in our stack. And some of the ways, I did advertise that there are some distinctions when you talk about machine learning, so I'm going to bring those up a little bit here. So, you know, persistence is hard. Ideally, you should not solve it yourself, and in particular, if you use the modern paradigm of DevOps, it's very hard to mix persistent and non-persistent parts of your stack. So better to push off persistence to a bunch of tools like Redis or Elasticsearch or Mongo or Minio that know how to do this. So, you know, something like Minio, it's not just a distributed blob. I mean, it is a distributed blob storage, which means you can have arbitrary many Minio servers, and they have data redundancy. They solve a hard problem you shouldn't reinvent, basically, or you shouldn't resolve. So the way we use this is we say, you know, we have in our stack, we have a bunch of parallel workers, and they all load up the NLP service because they're going to provide NLP services to clients. So a client might come and hit one of these guys and say, hey, create a model for me, train it to solve a particular problem. And it does that. But then the next client comes, and they don't know that they're talking to these things. There's some load balancer here. They're going to hit this guy, and they're going to ask it to use, they're going to want to use that same model. This is maybe not so unusual. You have a similar problem whenever you do any kind of web application with parallelization. But it's a little bit more complicated when you do NLP or machine learning or whatever, because the kind of data you're shunting around is a little different. So we solve this problem in a not very surprising way. We basically say, OK, I've trained this neural network here. What I'm going to do is I'm going to put it into some kind of a blob. So a neural network often involves a lot of different stuff you need to store. It turns out in Python, you can sort of put everything inside of a tar gzip in memory, which is quite nice. Then we just cache that in Redis. But we also persist it to Minio, because if your stack goes down and comes back up, Redis might disappear. Minio won't. And then every time someone comes and asks any of these guys for anything, they're going to first check all these caches to make sure it's there before telling the person that, hey, your model isn't here if it's not there. So you sort of transparently have these guys have no state. Their entire state is maintained in the Redis and Minio servers sitting behind them, right? I mean, I guess this is not too surprising. It's just, okay. It's just how you have to change things a little bit when you're starting to do the machine learning in a parallelized, scaled way. I have two more things I guess I want to talk about. One is a design pattern that I find very useful in building a stack like this, and it's something called the wrapper pattern. It's excruciatingly simple, but it's something you still have to sort of bang on the head of your collaborator sometimes. So it's very simple. Every time I import anything, if I import MySQL DB API, rather than using it directly, I will simply write a wrapper for it. And I do this with everything. Every time I use something that's not my own, I will write a wrapper for it. And it sounds kind of stupid and adds a little bit of overhead, but down the road it saves so much time. Because say someday I say, well, we have a problem with something going on in our MySQL API. I want to do very detailed logging of all the API calls. Rather than having to go and find out everywhere in my code where I've called the MySQL API, I simply go to my wrapper and I make those changes there. So it's a very simple pattern, but it's an extremely useful one. In fact, you can do even crazier things. You could say, well, actually, I want to manually shard my database, or I want to manually replicate my database. Again, you could do this pretty straightforwardly using a wrapper that exists there. You could just say, every time I get a call, I don't hit one database, I hit two databases for writing. So some of the things we've done with this, again, this is all about just maintainability of the code. In our initial version of the code, our logging and config was local. We would log to a file, we'd read from a file. Thankfully, because we used this pattern, it was extremely simple to switch to distributed versions of these things. And then the rest of the code didn't have to be changed at all. We just had to change a few lines of code here as well. And I know Python provides a logging service, and I still prefer to write my own wrapper to that, because this way I'm kind of under better control of what I'm doing. But we also use this for even higher level things like NLTK. So rather than saying in the past, NLTK parse sentences or NLTK get entities, we just had a entity parsing wrapper. And it used NLTK, but then when we want to shift to something else, we didn't have to touch any of the code except for that one piece of code. And kind of one of the craziest things that we did, which was kind of fun, was to say, at some point we wanted to interject user controls into the code. So we could dynamically, in the database wrapper, change the table names to views, and those views were imposed access controls. So without having to touch any of the code, we suddenly got access controls, basically maintained from a single place in the code. So it is a very simple pattern, but it's a very nice one. Maybe I'm telling you guys something obvious. If not, maybe I hope it was something useful to hear about. The last thing I want to share is maybe just some performance tips that I've come across along the way. Some of them surprising even to me. So there's another talk I think in this conference about Python performance tuning. I think it's interesting to go to. I actually checked out the slides from a free version. I tried not to overlap with that too much, but one of the most straightforward things, when people say Python is slow, it's true, but if you at least know how the Python native types work, you'll save yourself a lot of headache. So the Python native types are highly optimized themselves internally, at least within reasonable use cases. So know when to use, know what the difference between a set and a list is. A set is O1 access time, a list is ON. That's a huge difference if you build something large. If you're calling a dict and you say dict.items, this creates a whole copy of the dict. If you create, say, dict.iteritems, this is just an iterator. These things make a big difference. This can be, over 1 million times faster than this for a large dict. So, in fact, I've tried to check a lot of this stuff. This really also sometimes depends even on the particular minor version of Python you're using. Thankfully, we have timeit in IPython. This is extremely useful, and I basically use it all the time when I'm coding. So here are some examples that I have of very cute, simple things. So here I just created a dict of strings. It's a size million dict, and if you do something like 10 in dict, it takes 36 nanoseconds. That's just basically checking if a key is in the dict. I've seen a lot of code which uses .keys. The problem is that .keys is not, it's a list, not a set. So this is over 1 million times slower than that. So it's a really simple change, but this is something that can make your code, a lot slower. Let me go over one more example, then I'm going to just jump to the end. So this is this is something that hit me really recently, so this is why I bring it up. It's something very straightforward. I create a large array this is the kind of thing you do when you do machine learning a lot of the time. You create a large array in memory. It's a tensor. It has 10,000 indices, 10,000 in the first index, 1 in the middle, and 400 in the last. The reason it has 1 in the middle is that in a more general case, this might be larger than 1. And so somewhere in my pipeline, what I do is I sum over this middle axis. So there's some code like this in the pipeline. And if you run it, you see that it takes a couple of milliseconds. And that's fine because usually this thing can have more than 1 in it. But it turned out that in a particular instance, or for a large class of problems, this was always 1. And in that case, it turns out you can do something much simpler. You can simply drop this intermediate axis. And you see that, again, it's tens of thousands or hundreds of thousands of times faster to do it this way. So those little kinds of optimizations, they're really going to be very problem specific, and the only way to really know them is to use things like time it in a lot of detail. So I guess what I'd recommend is just use this a lot. Oh, maybe I'll take a quick opportunity to also advertise. I think many of you know that if you have bottleneck code, usually you have a very small amount of bottleneck code. You can often use something like Python to make that go a lot faster. What's much less known about, in fact, it wasn't even mentioned this morning, is Pythran. Pythran was actually spoken about in PyData here last year. That's where I learned about it. It's much easier to use than Python. It's a little less robust, but the main developer is extremely interactive. You can go on GitHub and ask him questions, and he'll help you out. So if you have a little snippet of Python code, and it's involves a bunch of, it looks like C, has a lot of for loops, a lot of numbers, you want to make it run 3 or 4 times faster, just try Pythran. I would definitely recommend it. It's a very nice library. Okay, I think I've run out of time, and I'm pretty much done. I'll leave you with this. Oh, by the way, just last thing I want to say. This is a really fun talk. So this is the author of GenSim. GenSim is a really nice package for text analytics. This is another sort of package, by the way, to talk about for machine learning. They do a lot of really nice things, and this is in Python. So he had a talk at some other Python conference asking if Python stands a chance in today's world of data science. And what he was basically asking is, compared to Spark and Java and stuff, can Python perform? And his library kind of stands out as an extremely performant library. So he tried to test analyzing Wikipedia using a bunch of standard text analytics algorithms with his library versus Java, Spark, MLlib, these sorts of Java machine learning projects. And what he found is he couldn't even compare them because the Java ones couldn't even finish the task. So really, he did a bunch of different things. I mean, it's a bit embarrassing. I don't know, maybe he didn't really know what he was doing, but he really said, I tried to run this on Spark. It just died out of memory error. His code had no problem running it at all. So in some sense, if you ever have someone giving you a grief about running large projects in Python, I would check this talk out. It's quite nice. And these are all also very nice references. If you guys don't know this, this is something from one of the main developers at Google. It's just a bunch of numbers you should know if you're ever trying to write performance code. How long does it take to access a disk? How long does it take to access something along a network? It's just a bunch of good little metrics to have. And I'll stop there.
Great. Thank you.